Hey everybody, welcome back to Tomorrow's Technicians live stream. Today sponsored by Summit Racing Equipment. Here with my buddy, my colleague Andrew Markell.
Thanks, Doug.
We are going to today be continuing our discussion of engine building. Last time, if you'll remember, we had Justin Wiedemann from Summit Racing joining us, and we talked about the business of the engine. The powerful, the heavy-duty stuff that goes down underneath at the bottom of the engine, the bottom end, building a strong bottom end. Today, as Justin mentioned then, that's the business. Today we're going to talk about the party. We're going to talk about the fun.
Air and fuel, so critical for an engine to run. And this is the nexus point right now for all of that because you've got fuel, you've got air, and access to the cylinder. So this really will predict the performance of an engine, and you can tune torque, you can tune horsepower. It all depends on the head, the camshaft, and even the intake manifold.
Great stuff. Lots to talk about. Before we get into all of the components, you can see an assortment of cylinder heads. We've got other components as well. Andrew, let's talk about the combustion process, that key component of what makes an internal combustion engine run, the four-stroke process. Walk us through what goes on.
Well, the four-stroke process, basically, it's suck, squeeze, bang, blow. So you have the intake stroke where the piston's traveling down. It creates a vacuum, and the intake valve is open. When the intake valve opens, air rushes in because you've essentially created a vacuum. So then that intake valve closes, and then you start to get the compression stroke. And when it starts to compress, that air fuel starts to reach the top of the cylinder, goes a little bit down, and then all of a sudden the spark ignites it, pushes down. That's your power stroke. And then when it's at the bottom, it starts to come up again. And then it opens up the exhaust valve, and that gas is pushed out. With this process, it's very simple. But there's so many chances to optimize the flow of the air and the fuel and even the spark.
Yeah. And with a multi-cylinder engine, that's easy to talk about when it's just a single cylinder, a lawnmower engine or something like that. You get into a multi-cylinder engine in one of today's high-performance vehicles. That's happening multiple times a second, many times a second. We talked about that, how many times it goes on. The precision that has to be maintained so those components work right.
Doug, you bring up a good point. A lot of these cylinder heads that are engineered at the OE level use what's known as a ruby quartz window into the combustion chamber. So they're looking at the flame front, they're looking at the gases coming in and out. They've always done this for almost like 40, 50 years, but what has really changed it are these cameras. They're able to slow it down quite a bit and look at that flow inside the combustion chamber, see where the turbulence is, engineer that out. And this isn't just OE stuff. A lot of the aftermarket suppliers for heads are using the same technology to look what's going on inside that combustion chamber.
Mm-hmm. So let's talk about the heads for a second. Different styles of heads. We have three distinctly different cylinder heads here. Let's start on this side and kind of explain the different components that we're looking at.
This is a gorgeous Jeep 4-liter straight six right here. And this head has, I want to say, started production in 1965, and it was used up until the 2000s. But with this head, it's all about torque. When this head is engineered, it's designed just to give a lot of torque. But this is great for people who are off-road. And then we slowly move into some of the more V8. This is a Hemi V8. And to where this has the valve side by side, this one is a little bit more interesting in that it has a hemispherical combustion chamber. Some of the Dodge folks will, it's not a true hemispherical combustion chamber, but what they did is they took the intake valve and the exhaust valve and they canted them at an angle. So you get better flow, better placement of the ports, and if you look at some of the pistons, they're a little bit domed, but this is all about the flow. And here, this is the late model Dodge head with both spark plugs inside the combustion chamber. Those are arranged that way to make the flame front propagate in a certain way under certain conditions. Let's say low speed, lugging the engine versus a high speed when you're trying to create a lot of horsepower. But the differences in these heads, they're still valves, they're still ports, but it's just this overall tweaking of the cylinder head design, the ports, how they're shaped, how the air flows through them, that has been slowly refined over the years. That Jeep head, 1965, you look at that combustion chamber design, over those next 20, 30 years, they did modify how that head looks inside. So it's these little refinements.
Yeah.
It's like people say the best combustion chamber. Guess what it was? For emissions, performance in some ways, Buick 3800, Series 2. And
Not exactly a new engine.
not exactly a new engine, but it's probably one of the best or more refined combustion chambers out there.
Great, great. All right, so we've got some of the Mopars here. We've got the Jeep, we've got the Hemi. Let's talk about this big one here in the middle too. Walk us through that one, because that one plays into the whole engine that we're looking at today as well.
This is a head off of an LS. We also have got the cylinder head gasket, but this is an LS. This is an evolution of the small block, and this is basically what you really think about. This is a fuel-injected head, and it's designed to be a fuel-injected head thanks to how they design these ports. Back in the day, these used to be called cathedral ports because, hey, it looks like a cathedral. But the reason why they're like this is the fuel injector. Fuel injector is probably about right here on this head. We can also see it on this one right here, to where it's designed to work with the flow and then down to the valve itself. So it's very smooth going into the engine with a little bit of turbulence.
So we've got the LS head. We've got an LS on the engine stand over here. Let's talk about, and because this is a fuel injected head, we've got the fuel injected intake manifold on there. Walk us through that.
So this is the basic components at the top end. First of all, we have the Holley EFI intake manifold, very nice. So inside of here, and this is sort of the neat thing, if Wes could get in here and take a picture, video of this, this is the intake plenum. And each one is designed to not exactly have too many obstructions going right into the intake valve. In fact, if you look at some of these ports, let me get this lined up properly, you could see the intake valve. And it's designed to be a straight shot. It's a nice plenum. You get great flow out of this. This one also works really well with turbocharged vehicles too. So we take that off so we know the air is coming in here. And also in this intake manifold, I'm going to hold this up for Wes here. Here are the ports for the fuel injector. So you have 8 ports for the fuel injector. And how they're angled and canted, a lot of science in this. So, and then we take that off.
And the fuel injectors mount to the
fuel rail.
To the fuel rail, which mount to the intake manifold.
So, and this is a great example of like what a performance company like Holley can do with an intake manifold, just by every little shape in here means something to an engineer to maximize airflow. There's other, if you looked at the stock manifold, they have kind of a different arrangement with plastic velocity stacks, let's just call it that would reside in here. But lots of engineering in there to get the most amount of air in there.
Right.
Because the most important thing to remember with any engine and any performance is the more air you can get into the engine, the more fuel you can burn, and the more power you can produce. Those 3 steps are so critical for modern engines.
Right. Now, there's another version, of course, of the induction process. Could be the carbureted intake manifold.
Yes.
Talk about the difference, how a carburetor works, and the difference with the fuel injection.
Oh, intake manifolds. There's a really great museum out there that has probably close to 230 intake manifolds for the Ford flathead V8, and all of them are unique to that engine. And those were designed around carburetors. A carburetor is kind of different. If you look at the different designs as they evolved, you have a single plane intake, which is essentially kind of what this is, for the fuel injection, but the single plane intake would have the runners like that going up to the carburetor in that square bore, and they would be drawing fuel in that way. Great advantages. I mean, a small block carburetor is the most reliable engine out there, and it sounds so good. It's a little bit simpler. But with, those intake manifolds, you had single plane. That was for a very narrow RPM range. Drag racers used it, some road racers used it. But for the guys on the street, they developed, I think it was Wieland or even Holley, the dual plane manifold. So essentially you had two sets of runners on top of each other going to the different. Mm-hmm. And that helped with tip-in problems, acceleration, but it didn't breathe the same way as a single plane. But it produced a greater amount of power over a greater spectrum of the RPM and also load on the engine. And then once you get into fuel injection, that really changed everything. And if you're going to be a technician out there working on, let's say, like a BMW, even General Motors stuff, Mercedes, you're going to see these intake manifolds that have flaps and valves, and those work to optimize the flow of air into a modern engine. You look at a Toyota engine, and it's got a change in the runner length that they can do through the intake manifold. And then on top of that, they have the tumble flap. And this is it would be right here. And what it does a great thing with the Toyota engines of blocking off part of the port. So it increases the vacuum as that cylinder is driving down. And it sort of improves the overall turbulence. But with these anti-tumble valves, that's what Toyota calls them. BMW, GM, Ford use those. But that's, intake manifold 3.0 almost.
Mm-hmm. Right.
But it's what the technicians will be dealing with in, today and down the road.
In a lot of cases, the students watching today are going to be facing those as soon as they get out of school, if they're not already seeing them in the classroom.
Definitely.
Yeah. So, okay, we got the fuel coming in.
Yep.
Now, once it gets through the intake, comes down into the cylinder head. What are we talking about? Talk about the components that you're going to find in the heads.
This is, once the air is about ready, you see an exhaust valve, or it's actually an intake valve. And this opens, and that air and the fuel may hit the back of the valve and then stream down. So with this, it's critical that, number one, where they can optimize, is the chamfers on the side of the valve, and also the head itself, and the valve seat. So that's a main sticking point for turbulence and everything else. And if you can do, you can hear 3-angle, 5-angle, 6-angle valve jobs. The reality of it is they're just trying to smooth out that airflow into the cylinder. With a lot of these combustion chambers, it's it's a very well-engineered space. And you may think that porting it, you hear that word. Porting, what it is, in case students haven't heard of it, is where they smooth out the intake and the area around the intake valve. And this supposedly creates better flow. You can also optimize this for the size of the port. You can increase and decrease. Porting it's an art. And with a lot of this stuff, you can make a bad painting. Let's just say it that way. I've had this experience once where I was porting a head. I thought, oh my gosh, this is going to be the greatest flowing head ever. It's actually from a Datsun that I had. And, I was there with my die grinder, making that hole bigger and bigger, getting it to match the gasket on the head, and then also the intake manifold. And you don't realize that inside here, behind these passages, are, chambers for the push rods to work. And there's also cooling in there.
Yeah.
So, I thought I was doing the greatest job ever, and then I punched through the side of the runner there.
A little JB Weld, you'll fix it right up.
Actually, That's what I did.
Yeah. Well, one of my former the writers for one of my other magazines I used to be on, Joe Mondello, legendary Oldsmobile cylinder head guy, would talk about porting the heads and what he did to create NHRA legends Roland Leong, and some of those amazing drag racing legends. But how precise you really need to be. A lot of times, most times, let's not even say a lot of times, 99.99% of the times, the engineer who created the head probably is going to do a better job than you are, but making things smooth a little bit. But
it's definitely an art where people sense the flow of air and senses. I mean, you look at some of the NASCAR heads from the 1990s and early 2000s where they had to use a stock block. And this is probably the most interesting thing, is they would take the head, fill it in with welding. I think it was a TIG process. And then they would change the placement of the ports, move it over this far, you do this, change the exhaust flange, and they were basically adding metal to the head and then machining it to their own specifications. And those guys, amazing guys, you know, were Brock Yates. And, Robert Yates.
Robert Yates, right.
You know, those guys. Bob Glidden, he was another one who did a lot of those cylinder head things that just it would blow your head. Bob Glidden was an HRA, pro stock guy.
Yeah. Well, the guys who know what they're doing can do amazing jobs. I wouldn't want to be digging around in there. So we've got the intake valve. What else do we have here? We've got the exhaust valve. Talk about the difference between the valves.
So with this, actually, this is our exhaust valve over here, and this, you got the intake and exhaust valve inside the head. They can be different sizes, but if you're dealing with like a 4-valve engine, you know, they may be the same size relative. With these, you look at, before I drop anything here, with these, you know, this is, let's do a quick little anatomy lesson here with Wes. So this is your intake valve on this head, and this is your exhaust valve on this head. And if you look in here, you could see in the inside of the exhaust port, you could see the sleeve for the valve and everything else. So intake and exhaust. The exhaust sometimes is smaller, sometimes it's the same size, depending on the number of valves. And if you flip it over, you've got this area right here. So you have the valve springs, the valves, the valve keepers, and the valve retainer. With these,
We have some examples here.
this is a whole nother thing with tuning this, is you could be tuning the spring itself to make sure that it works under certain RPM ranges. You can even lighten some of these, you know, racers who don't use that much RPM, you know, they use a weaker spring, or it could be a harder spring because you're trying to get up to the higher RPMs like 9, 10 grand, and that will influence the spring rate of these. And then the valve itself. I mean, there's so much, this is geometry. I hate to bring up a math topic to the students, but this is all geometry. You look at the rockers, you look at the valve, you look at the position of the rocker on top of the valve itself, and there's certain angles that they need to pay attention to. And even setting up the valve train, make sure you're picking the right components. Make sure that you're doing your measurements. Make sure that all the parts are compatible with each other. Because that geometry, once you start to go outside the norms, you start to get failure with a cylinder head. And you need to make sure that all of it works properly. Because you can create something that could bind, it could have other issues where essentially the valve will float at higher RPMs. When it floats at higher RPMs, what we're talking about is this spring will actually stay in this, like, I don't know, it's not able to control the valve. So essentially, the valve starts to float. And this is when you hit like 5 grand and, you know, on, you know, let's say a GM Iron Duke. But some engines can engineer that out and they can rev up to 10 grand. But this geometry is so critical. And consulting with like who you're buying parts from, like Summit Racing, they can advise you of a valve train that will work great for your application.
That's a great point. The complexity, the geometry, the complexity of the valve train. It looks, you know, from the outside, cylinder head looks so simple. Air goes in, air comes out, fuel goes in, fuel goes out. But there's so many different components that are within it and how to work together. Talk about the rocker arms, you know, how how they interact with the springs, the push rods, the components.
So rockers are critical for taking the force that's pushing up by the camshaft and moving that over to the valve and pushing it open. We see some up on the screen right now. I think I'm trying to remember who the manufacturer of these is, but with these, that geometry is critical. And like these, they probably have needle roller bearings inside the fulcrum, and they're designed to work more efficiently. Mm-hmm. In other words, you're wasting less horsepower getting the engine turning with some of these rockers, and that's how they change the geometry. And that's why you could use a stiffer valve spring, even like a different push rod. But you got to do your math and your research on some of these builds, or else you're going to come in a situation where it seems to run great in the garage and everything else. You flip the throttle a couple times, it feels good, but then when you get to a drag strip, it falls flat on its face, which is not good. And that could be just strictly to valvetrain geometry. Inside of the valvetrain itself, the camshaft, that's another critical thing in terms of duration. How far it can lift and duration can impact also the rocker design, depending on how far it's pushing it, the height. So you really got to measure stuff and make sure it's within tolerances.
Camshafts, there's a whole nother topic. Where they are, how they work, what they're composed of, how they're ground.
And another bit of math. This right here, gaskets. When you're building an engine and bolting on your top end, you have to make sure you're using the correct gasket. But it's also the height of the gasket and the thickness of the gasket that can change the compression ratio of an engine. Not too much, but it's enough to warrant a lot of cylinder head manufacturers to make a couple different cylinder head gaskets for a given application, because you can take stuff off the head after you machine it, add it back with a gasket, still keep your compression ratio in check, or you can use maybe a little thinner of a gasket or shave stuff, so you can change your compression ratio.
Talk about the gasket construction. This may be a little different construction than some people are used to seeing. It's not the cork gasket that you might have thought seals the block in the head.
This is a performance head gasket for an LS, and it's what's known as an MLS type head gasket, or multi-layer shim. So you have spring steel inside of these, and they're coated with a rubberized coating that creates that gasket type material that can seal the cylinder head and also the gasket itself. And with these gaskets, as you start to move up the more pricier ones, or that can develop more horsepower, you start to see stuff like laser welds on this ring right here, or you may see, oh, got my hand there. You may see some rings or a gasketed type arrangement that help to seal this gasket under extreme stress.
Talk about the, and kids, don't do that.
Yeah, do not do this with your head gasket.
We've learned something today. Talk about the evolution of gaskets, if you can. How they've gone from the old cork, the old paper, the old felt blanket gaskets to what we're seeing today.
Back in the day, you did have replacement gaskets and some things, but a lot of part stores sold gasket material. You'll see it now and then in certain part stores. And it's a roll, you roll out, and you take the old gasket and you start cutting. That was like back in the day, pre-World War II, let's just say that. And you had like these special punches that you used to knock out holes for bolts. But then it evolved further and further, the Ford engines, the Chevrolet engines, and everything else. You started to get pre-made gaskets that were typically, they could be a fibrous type material, like you even have asbestos embedded in them. But these always had limits to how much compression you can get out of it before it was forced into the opposite cylinder. With a lot of these gaskets, the main failing point is right here, and right here, to where it gets pushed by the combustion pressures out of the way. And that's what kind of spurned the MLS gasket, is because it could take a whole lot more compression. And racers were using this before. Copper gaskets. Cylinder head gaskets that were made of copper have been around since, God, the 1960s for drag racers. And they use this because it was soft. They put a little lip and ring around, where it would interface with the combustion chamber to contain it. So, but yeah, it's been a slow evolution.
There's been a lot of other things, as the copper gaskets, the ringing of the cylinder heads that are more appropriate for high horsepower race engines than necessarily, are a good street engine. But there are a lot of other things that engine builders do to seal that engine, because the difference between the block and the heads, we've got cast iron blocks, we've got aluminum blocks here. Talk about that, the requirement to keep those heads sealed tight.
Bolts have changed quite a bit. You look at the types of bolts that were used 25, 30 years ago, they were typically larger than most of them. And some of them did have a torque angle and some of them were torque to yield, but we've seen this evolution of that fastener becoming more able to generate a clamping load that stays consistent through the entire life of the engine. And that's why they're using some of these torque to yield bolts that require a certain amount of instructions and procedures, because usually you've got a torque setting, and then on top of that you've got an angle to add. And this is the cool thing about it. Most of the old head gasket bolts, they just created tension and friction with just the threads, and it would hold it inside the head to the block. Well, with torque to yield, essentially you're stretching that bolt out, and that creates that clamping load that will stay consistent. They do get it wrong. If you're out there as a technician and you're dealing with like a North Star V8, they undersize the bolts to maximize the cooling passages inside the head and to avoid those 4 camshafts. And those smaller head bolts created a problem because it couldn't contain the gasket and keep the head secure. And there were endless problems. I think Cadillac even had a recall on it. But the fix was a larger bolt. So definitely evolving.
And the difference between head bolts and studs.
Okay, that's a critical thing. If you look at some race cars, they use studs. And this is just it gets a better bite and better control and stretch of the bolt. It's a different design. Companies like ARP, they have a vested interest in making sure that head bolt works for a certain application beyond a certain point that the OEs decided to. So that's why they use a stud. Bolts, it's a bolt. Lots of OEs use that. They'll use it with a washer just so they're not going up the surface. But typically you're going to see those bolts, those will be used for production cars. Those ARP studs and nuts, those will be used for performance applications.
Is there a different installation process between using them? Can you decide, I'm going to put studs in, or I'm going to?
You can, but make sure you're following the precise instructions of the fastener manufacturer. These kits can be purchased for head bolts. If you have a LS, a small block, a Hemi, and you start going through that Summit Racing catalog, you'll see a whole variety of bolts in different prices. Studs will typically be more expensive. It'll come as a kit. And for racers too, if you're pulling that head on and off, you want to deal with a stud and not have to line it up, get a bolt in, and then force it. Studs just make it easier when you're
The
doing
stud,
this.
you just drop the cylinder head on and you
Fasten it down.
fasten it down. Is there a horsepower advantage or compromise between the two?
I think it's a reliability thing.
Okay.
They always say with racing, you've got to finish to win. If you're dealing with a head that's kind of doing weird things on top of the combustion chamber, you're probably not going to win.
What are some of the challenges that engine builders, whether professional or amateur, can face when it comes to the valvetrain?
Parts compatibility. That is so critical for with a build that you're doing, is making sure the rockers work together with the push rods that works together with the camshaft, and the cylinder head works with the block. That's a big issue, and you know, that's where you got a partner in Summit Racing, because you know those guys on the phone and behind the desk at their retail centers, they know what they're doing, and they could say, well, you don't want to do that because this would cause this issue with the engine. Piecing something together can get you into trouble. That's a big issue. Also, you know, the machine shop, making sure that you get your heads and your block, if you're doing a refresh, that are perfectly square, knowing what they did to the block. And that's another thing of reading that build sheet in the machine to figure out how much they took out, how much you're going to have to change up stuff for the valve train, and even the connecting rods and the head gasket.
That was going to be my next point. Actually, you led us perfectly into it. When they've surfaced a head, you can get heads at a salvage yard. You can get heads a lot of places. You can get blocks a lot of places. And the surfaces just aren't compatible. They're not flush. They're not flat. So you get a machine, you get the work done, and yeah, you may lose what seems like an infinitesimally small amount of metal. And yet, that's going to be the difference between success and failure in a lot of cases.
With these, you cannot set this on a belt sander and get a good surface. This has to be square and true, because, you know, you're dealing, you know, I've heard things of 10,000 PSI under certain conditions when you get that flame front going against the gasket, and that's what causes it to fail.
Explosions. I mean, those are serious explosions happening multiple times a second.
Yeah, and that is so critical that, you know, this is square, it's the right tolerances, there's no warp in it, and this is the thing you're probably going to run into in the field when you're as a technician, is you may think that Toyota, that Ford V6, you know, I just got to take a roll-lock disc and like polish it off, and it'll be fine. It'll get to the customer, you know, until they need to sell the car. But the reality of it is you're doing them no favors at all. If you decide to machine it yourself, you could cause issues. But the biggest thing that happens with a lot of these heads is you'll have someone who will take a roll-lock disc and they'll be in this area, they'll be cleaning up that old gasket material that's there, and they'll start with that roll-lock disc getting a little too aggressive, and they'll round off some of these surfaces. When they round off some of those surfaces, they cause a leak because the gasket is only sealing on a very small amount of it instead of that full square broad area. That area that's been rounded off by a roll-lock disc or even something more aggressive can cause big issues.
So how important is it, Andrew, for the left side of the head, the left head and the right head to be compatible? I mean, do they have to be exact? You know, what if, you know, this head you've had to resurface this? Do you balance it out with the gasket? Do you balance it out with the push rod length? How do you justify making that V perfect?
Yes, that is part of the machining process, making sure, because when you change the deck of an engine, you're changing how the crankshaft operates and the distance the pistons come up. So you've got to be careful of that. You know, this is a big contention if you're working as a regular technician at a shop, is a lot of the recall stuff you're going to read in TSBs. They'll advise only to replace one head. It's typically a good to replace both, because, you know, this is a Ford Intech V8, early 2000s that they produced this engine, and they had a great TSB out there because it was burning the exhaust valve. And when it was burning the exhaust valve, technicians and some of the warranty people were calling for both heads to be replaced, which is what you should do. But Ford figured out the procedure to where they only had to replace one, and it was typically on the driver's side. So yes and no, but best practice, replace both, machine the block, make sure everything's square and true.
Square and true. That's right. Again, it comes back to math. Talk about that in the classroom. You know, for our students who are watching this in the classroom, and the teachers preaching math. What kind of math? What do they need to, what do they need to be paying attention to? What do they need to be studying?
Okay, it's critical basic math. positive, negative integers, division, multiplication. You'll be using all of that to do some of these equations for compression ratio, and also some of the geometry, figuring out the angles for it. Very simple. And then geometry, figuring out the space and area of, let's say, a combustion chamber, or how far down the cylinder goes to figure out, what's the displacement of the engine. So those are two critical equations that you could probably, your instructor can probably, give you a pop quiz on, or tomorrow's technician, we could probably come up with a math quiz. I think that we've discovered a whole new area for students. Algebra for automotive, which we won't call it that, but you've got that, every little thing is math. It comes down to even, your compression ratio and what type of fuel you're going to use and doing your research.
Right.
And, if you're building your own engine, you're learning so much that you could apply when you're working at a shop.
Yeah. When you talk about the math, you talk about things such as octane ratings, you talk about, fuel quality. Let's get into that a bit here with all the different styles or different types of fuel that are out there. Bio, diesel, E85, E15, gasoline, different levels of gasoline. How do you know what you need for your engine?
It's a matter of how you build it. So if you're going to go for an E85 engine, or, you're basically having to, okay, first of all, you're changing the fuel pump in the tank. Then you're changing the injectors. Then you're changing the ECU for the timing, just because it may be a lower octane rating from E85, but it's got more power to it. And you'll typically have to inject 25% more E85 compared to gasoline at the same octane rating. So you're building that into the engine, the fuel trims and everything else. Carburetors, it's a little bit tougher because you really got to adjust the jetting. But with E85, you're building out the fuel system and the fuel trims. So it acts the same way as gas. You just got to make sure that it gets into the engine at the right quantity.
Yeah. So it's not just the engine; it's the rest of the fuel system that has to be addressed when building an engine. These parts obviously don't stand alone. We look at the integration and the interaction between all of the parts within the head and within the engine. You just think that it just extrapolates out throughout the car. It all works together.
I mean, something as simple as, I think my famous math problem that I put online was the brake booster volume and how much force can a brake booster provide, and that was, that was pi. So figuring out that surface area. But don't be intimidated by the math. It's very simple. There's probably even worksheets available out there from the parts manufacturers that we can even provide. But yeah, it's definitely a learning opportunity.
Yeah. In the real world, Andrew, you are director of editorial or director of technical content for the automotive service group here at Babcock's, which includes brake and front end, import car, underhood service, shop owner. You also do tech shop, tire review. You've got your hands on a lot of different brands. Talk about real world examples of things that go wrong in the valve train, whether they're domestic, whether they're import, whether they're diesel, things that our viewers should really maybe kind of be thinking about facing once they're in the real world.
Boy, that's a tough one. Once you get out of school and you start working for a shop, chances are you're not going to be doing an R&R on an engine where you're pulling off the head. You might be getting into maybe a timing chain or a timing belt, and that's your entry or your gateway into engine repair and really looking at the stuff. It's all about following a lot of the procedures if you're working on like a non-performance car, like a Toyota, Honda, and making sure that everything works properly and that you're using the correct torque settings and specifications. So follow the instructions. That's probably the most important thing that I've kind of learned, because there's certain things with like a head. The sequence that you take out the bolts on certain engines can influence if that cylinder head comes out warped afterwards. So it's the general assumption for most technicians is when you remove a head, you do outside and then work your way in. It's like the opposite of if you were installing the head bolts. Head bolts typically start in the center and then you start to work your way out. The worst thing is you start in a corner and work your way inward.
What could possibly go wrong?
Well, you got to look at these specifications on a lot of these newer engines because they're highly engineered to get that clamp load just right. And a lot of these
An even clamp load.
I saw one procedure, it was close to 5 to 6, torque down steps. But just be aware of those, don't try to do it on your own or figure it out. But that's a big thing, making sure you know how the head bolts work. And just general inspection, because you could spot every little thing. And this is another reason why you take it to a machine shop for a head, is they can magnaflux it, they can make sure it's not leaking. There's other products out there that you can use to make sure that this is not cracked or this area between the valves is not cracked. That's critical. That is very critical. That inspection. And then using the proper chemicals. Guys kind of forget that certain RTVs and certain sealants may not work with an oxygen sensor, or they may not seal properly under certain conditions underneath the hood of a vehicle. So looking at the service information, and you'll notice like Motorcraft, German manufacturers, they'll have this famous line that says, their part number, Motorcraft 659 BPS something, or equivalent. And you may find out that that's a Permatex product or something else out there. Making sure you're using those because they impact the engine as far as how the head bolts torque down. Because if you use the wrong, anti-seize or anaerobic compound, it can change how a head bolt works, which is huge. And then also fuel-injected engines, you could poison an oxygen sensor if you use the wrong RTV or silicone-type gasket material. And just, that's one mistake I've made. I've poisoned oxygen sensors.
The wrong product, the wrong amount of the right product can be just as damaging.
Yes. And, it's critical because you can wind up in that situation. You don't have the right sealant on a head bolt, and all of a sudden the engine's overheating. You're like, what did I do wrong? So that's probably the biggest piece of advice.
You did mention something earlier that we just sort of skipped over, and that's an important part, timing. Let's talk about engine timing, the relation between the top end and the bottom end.
It applies to a lot of stuff you'll be working on out in the field. The timing, if you're getting ready to time the camshaft on this engine, you're going to have a cam timing wheel. You're going to line it up with the crankshaft and make sure that everything is within tolerances. It gets actually more complex if you're working on a production vehicle, because that production vehicle, it's going to have variable valve timing, and that could change on how the engine is timed up. And then on top of that, you got chain or belt, just making sure that everything's in check. And I know I've said this probably about 20 different times in this session. Check the service information for the proper procedures, because to lock down some of these engines, especially the variable valve timing phasers, it takes special procedures or locks or special tools to do that to make sure the job has been done right.
Yeah. Phaser sounds pretty high tech. Star Wars even, right?
Well,
but talk about variable valve timing. Because you're going to be facing variable valve timing once you get out into the field.
What it is it changes the timing of the camshaft. It can become advanced and move this way, so you can have, basically, you could buy infinite number of camshafts for your vehicle that are already installed. And it changes the timing, the duration, some of the stuff more complex, Honda, BMW, they even changed the lift on the camshaft by just shifting the camshaft over and putting it on a different set of cam lobes. And, that's the biggest challenge. And, as complex as you make it seem, some of these racing engines, the production engines, just the complexity alone it's amazing.
Right. And when you start talking about variable valve timing, the things that you can do yourself to screw up the variable valve timing just by using the wrong fluids.
Yeah.
the wrong oil, the wrong gasoline, the whatever, you can do things to really impact so that the variable valve timing does not work.
That's the most important thing to say also for new students and technicians out there is to understand that the valve train in some ways it's hydraulic because you've got lifters inside that take up that gap in regards to if the valve changes position and that lifter interacting with the camshaft. That's oil pressure. And with variable valve timing, you're dealing with it even more. You've got that phaser that has oil on either side that they control the movement of the camshaft. And that is so critical in how fast it's happening on a lot of engines now. It's pretty amazing. Yeah. And if you put the wrong grade oil into it, since it's a hydraulic system, you could be making it more sluggish, actuate too fast, and it knows because it has a camshaft position sensor and also has a crankshaft position sensor to say, something's not right here.
Yeah. Yeah. What you think you know about oil quality, viscosity, you may not understand oil anymore.
Yeah.
I mean, oil is a complicated topic that's important to have a handle on.
We have a question from Dan here that came through, actually on, I think it might be, YouTube. He's wondering which is a better engine, a pushrod V8 or an overhead cam 4-cylinder 6 or 8?
Better is a tough word to answer because it depends, but
is it more economical? What's the engine being used for? That's the beauty of a pushrod V8 is that pushrod V8, single camshaft, a bunch of lifters, a bunch of connecting rods, 16 valves typically. It takes less force to get that moving off the line. Let's say it's going from idle to 3,000 RPMs. There is less drag on the crankshaft to get that moving. To where let's say an overhead cam engine, it has to move 2 camshafts, more valves, so that low end torque and the power produced down low is a little bit different. But, here's the big but, if you take a multiple valve head, 3, 4, 5 valves, in the case of Audi sometimes, you're getting it better flow at higher RPMs, which is where they're kind of making their engine, tuning it to develop that power, usually on a higher end, 3,000 to 6,000. It's not going to produce the same amount of torque as a V8, but it's going to definitely be more efficient. But, so which is better? Depends on the application, the vehicle, the weight of the vehicle, what you're using it for. I mean, you wouldn't want a 4-cam V8 in, let's say, an off-road truck, but that may work on a road racing vehicle.
Right.
So.
Right. Again, let's get back into some of the real world examples of what can go wrong in the engine. When it comes to, you mentioned at the beginning, the way the fuel hits the backs of the valves. There are things, today's fuel, today's engine configurations, where this can become a little bit of a problem.
Well, I mean, with these valves, you really look at, I got my own.
Yeah, there you go.
This is great. With these, let's say, 1950s, 1960s, you had a carburetor that was running rich and it was throwing fuel on top of here. And if there were any carbon deposits caused by the engine itself or the heat, those were kind of washed away by the fuel mixture. And then port fuel comes along, it's washing those off. But carbon can build up on these on direct injection engines because there is no spray. It's spraying directly into the combustion chamber, and that can cause carbon deposits. And when you cause a carbon deposit on one of these, you cause an obstruction that can cause turbulence inside the cylinder. And this is when you start to get those, let's say it's a Ford, I think it's their 2.3 or 2.4, where the 2 internal cylinders would start to get those carbon deposits, and you'd get misfire codes on cylinders 2 and 3. Well, it's because all of this oil and carbon built up on the end of the valve and prevented that fuel and air, the air from getting inside the engine. So with that, the Ford's correction was they changed their PCV system, and they also changed the ECM programming and calibration to, make it less stressful for the engine, and, so the valve itself was spending less time inside the combustion chamber, because those carbon deposits, they're actually caused when this valve goes in and you have those gases inside the cylinder, and they would build up on there, and then they pull back out, they'd stick. So that's, when this goes in, it gets dirty. Comes out, it blocks air.
Yeah. Is that more a case of the engine configuration? Is it more a case of the valve design? Is it more a case of the fuel that you're using?
Well, we covered this before with the variable valve timing. So with variable valve timing, you can control duration and also the timing. So you could leave this valve open during, let's say, the exhaust stroke. Mm-hmm. You could just bump it up a little bit, not that far, and then it could add air into the combustion chamber, or so that air can be used later on down the road by the catalytic converter. So a lot of auto manufacturers, and you may see a Honda TSB on this with their V6, to solve this problem, basically what they did is they changed the timing of the camshafts. So it wasn't as efficient as it was before, but you didn't get the carbon on the valves. Mm-hmm. And that was just strictly changing how long it spent inside the combustion chamber when it was pulled out, and certain things under the valve overlap too can make a difference.
Yeah. Talk about how the valve train has changed over the years, the differences that you've seen maybe since you've been working in the industry. Obviously, we don't want to go too far back, because we definitely could. There have been changes from the early days of performance in the American auto industry. But talk about some of the changes that you've seen.
Looking back on some of my early vehicles, my dad was a General Motors employee, so I was very used to that valve train on, the Pontiac 2.5 Iron Duke, and then also the 60-degree V6. Mm-hmm. Very simple. You had rockers that were stamped. You had push rods that were very simple. But then the evolution of it all, I think I was working at a Nissan dealership, and we started to see some of the Infiniti stuff and some of the Nissan stuff come out with variable valve timing, strictly on the intake camshaft. That was a shock to a lot of technicians, because it was one more system that could fail. And, other manufacturers in the 90s and early 2000s started to get variable valve timing as engines would phase out and new platforms were brought in. And then on top of that, we had, the phaser also moving over to the exhaust cam now. Mm-hmm. Because before it was just the intake, you look at BMW, Vanos, and everything else. And it just was changing, 1 to 2. And then we saw some of the unique things that kind of Honda pioneered with VTEC, as far as moving the camshaft or moving the lifter over to change onto a new lobe on the camshaft. Audi has that technology. A lot of auto manufacturers do that. BMW does it quite a bit lately. But yeah, that's the variable duration and variable lift systems. And then cylinder deactivation. That's another thing that you're going to see on a lot of these performance things, either eliminating it or getting rid of it. But cylinder deactivation on the LS, again, hydraulically. Yeah. It controls the lifters and the position and everything else. To deactivate a cylinder, it could go to 4, 6, or 8. And that's been, the evolution. And then, the latest evolution, I drive one of these cars, is a Fiat that has the multi-air system. I know I'm getting a lot of boos out there in the audience for when I said the word multi-air, but that...
And not as many as you said electric.
Yeah, yeah. But that, basically, it has no intake camshaft. It just has an exhaust camshaft with extra little lobes on it that power an oil pump that control the position of the valve. I kind of think there's something coming that's going to come off after that, because I don't think it's a perfect system, the multi-air system, but basically you're using oil to bring it in, bring it up, and that little tiny, there's 4 different oil pumps on top of the engine. They can generate as much as 1,300 PSI to move that valve up and down. And it's all done through electric solenoids. So something's there. I mean, there is that talk about the electromagnetic valve engine. Koenigsegg engineered the smart valve technology. So basically, you've got a big electromagnet at the end, and it pulls it up with magnetism. They've gotten that to work, so maybe that could be the future. I'm sure we're going to have internal combustion for a very long time, and I think that we're going to see that pretty soon.
Yeah, yeah. One of the things that we didn't talk about, but when we look at evolutions and changes, turbocharging was popular for a while, and then it got a real bad rap. And now it's back, but we may not even know that it's back.
It's amazing, and that comes down to the power of the computer processor. We talked about earlier about the speed of the cameras and digital cameras, seeing the flame front inside the cylinder. But that ECU underneath a vehicle, it's gotten faster. So it's able to manage a lot more things underneath the hood of a vehicle, a whole lot better. So that's going to be a big issue is, managing valvetrain, because it's now electro-hydraulic more or less, and other things inside the engine. But yeah, it's
the changes with power adders, turbochargers, superchargers.
Oh, turbochargers. Yeah, that's what you're talking about.
Yeah.
Again, this goes back to that three-thing rule. If you can get more air into the cylinder, you can burn more fuel and make more power. With the turbocharger, you're forced induction, even a supercharger. So that's building up a lot of power inside the engine because you got more air, you can burn more fuel, make more power. But they've really changed as far as how the turbo operates because you have an electronically controlled wastegate, blow-off valve. Also, the throttle angle is controlled by computer, so you're getting a lot better efficiency out of the engine. And you're looking at like a 1.6 liter engine cranking out enough horsepower that the customer thinks it's a V6. So that's, and it's thanks to a turbocharger. I think they're going to be around for a very long time this time.
They've certainly don't have the poor reputation that those turbos of the 80s had.
Yes, those turbos of the 80s, if one of your instructors or anybody else remembers some of these vehicles, they were absolutely peaky on power. They would have a very limited range where the turbocharger would come in. It wasn't very well controlled. The fuel injection systems couldn't keep up with it. So they kind of took them off the market because they were causing issues with reliability.
Everyone knew the turbo lag, and you just sort of accepted that.
Yeah, but on top of that, we figured out how to make a turbocharger last underneath the hood of a car. The oil supply. So that's really changed. If you drive a turbocharged vehicle, you'll notice when you turn off the key, if you just listen, you'll hear probably a couple different pumps circulating oil and coolant around that turbocharger just so it doesn't coke up like before. So, but that's that's really important as far as making that turbocharger last.
Let's talk briefly as we're approaching the end of our time together about how it all gets started. The ignition, that flame that starts the process.
Okay, here is your tech tip of the day. And I'm going to borrow this one from NGK. You can buy their plugs at Summit Racing. I'm not endorsed by them, but this is given to me by one of their trainers. Look at the specifications and procedures for installing a spark plug on a vehicle before you install a spark plug, because a lot of these newer engines, they're essentially indexing the plug 90 degrees to the intake valve. And they're doing this through the number of threads on the spark plug and then also the torque setting. And there may be another thing where you just turn it like this, but they're indexing the plug is back for production engines, which is kind of cool. But that's your thing, is make sure you're looking up the specifications for a spark plug when you install it in your head to make sure that you've got the angle right. Because that side electrode and how it's turned can influence how the overall flame front is propagated inside the cylinder. And if you have the wrong plug that's turned the wrong way, it can cause some turbulence, and that could be a lot of issues for the driver.
So don't just tighten it down, get your gorilla arm going and tighten it down as much as you possibly can.
Yep. Just keep in mind the spark plug manufacturers and the OEs have engineered into that system a way how it's not going to be perfectly centered like you assume, like how some of the indexing stuff, but it gets it pretty close.
Yeah. One more component where it all works together. Just like us working together here to talk about the upper end of the engine, Andrew Markell, Director of Technical Content with Babcock's Media. I'm glad you joined us today.
you.
Thanks for being here. You out there in YouTube and Facebook land, remember that on December 14th, we'll be hosting another live stream with Summit Racing. This time, it will be batteries and alternators. So lots of interesting things that you may not have thought about when it comes to powering this engine, powering this car.
You'll be that webinar or the training live stream. Sorry about that, and I get all those ones mixed up. It's going to be a great way to think about how the alternator works with the battery, and especially on modern vehicles where that alternator is very well controlled, and you're going to be able to understand, what's the charging voltage of the system, and it's a different perspective on starters, alternators, and batteries.
Lots of great things to come. Thanks for joining us. We look forward to seeing you again December 14th. Till then, have a great weekend.